This is our lecture number 15, and we are going to cover the topic of Introduction to Dynamic Analysis in this lecture. So this is not the actual dynamic analysis, this is just the foundation of dynamic analysis. It means we will quickly recap what we already studied in the subject of dynamics. Okay, so there are a few terms which needs to be refreshed before going into the actual dynamic analysis. So these are the topics which we are going to cover in today's lecture. First of all, we will see what is a dynamic analysis, and after that we will see the Newton's law of motion, which are actually governing the dynamic analysis. Then we will see the two subclasses of dynamic analysis or dynamic problems, which are forward dynamic problems and inverse dynamic problem. We will see what's the difference between these two type of dynamic problems, and what type of problem on which we will focus in this subject. Okay, then we will discuss different mass properties. There is something wrong with the properties spelling, but you know what's the spelling of properties. So we will discuss different mass properties, which include the mass moment of inertia, which is also known as second moment of inertia. Then we will discuss the radius of gyration, radius of percussion. So these are the different terms which you already studied in dynamics course, but we will refresh so that you know the basics of the dynamic analysis. Okay, so now we will start our today's lecture. So what we have till now, we already did the kinematic analysis. It means we carried out the position analysis, we carried out the velocity analysis, we carried out the acceleration analysis. And what's the purpose of carrying out the kinetic analysis? The purpose of carrying out the kinematic analysis is to get the acceleration value. We need that acceleration value because we need to calculate or measure the forces and torques which are actually acting upon the system or the mechanism or the machine which we are developing or which we are analyzing. Okay, so why we need to calculate these forces and torques? Because with the help of these forces and torques we can calculate or we can carry out the stress analysis, and while doing so we need to calculate the yield strength, the stress and strains. Okay, so all of these are material dependent properties, and we can calculate all of those parameters only if we have the available forces. Okay, and we can only calculate the forces if we have the acceleration available, and we can only get the acceleration if we have the velocity and position available. So this is the complete cycle of analysis which we are going to cover in our course. So some of the portion we already covered, and now we are in this portion, the dynamic analysis, and this is something which we are not going to cover in this course, but this is something which you already studied in different subjects like mechanics of materials and maybe statics. So these are something which you already know. So with the help of these forces you can easily carry out this stress analysis and decide whether the design which you proposed gonna work or not. Okay, so what are the outcomes or what are the outputs of kinematic analysis? So those are the linear acceleration and angular acceleration. So those values will go to the dynamic analysis, or we will use those accelerations in the dynamic analysis to calculate forces and torques, and these forces and torques will go to the stress analysis to calculate these parameters, which are yield strength, stress and strain. Okay, so in kinematic analysis we already know the position, we already carried out the position analysis, we already carried out the acceleration analysis and velocity analysis, so we already know all of these. But what's missing in the dynamic analysis, we still don't know the forces and torques. Okay, so we are going to calculate these forces and torques in the dynamic analysis. Before doing that, we are going to refresh some fundamentals related to the subject dynamics. Okay, so first of all we will discuss some laws which are basically governing the dynamic analysis. Okay, so those are obviously the Newton's law of motion. So we will quickly recap those Newton's laws and we will see how those laws can help us in carrying out the dynamic analysis. So these are the three laws which are going to be used in the dynamic analysis. The first one is a body at rest tends to remain at rest, and a body in motion at constant velocity will tend to maintain that velocity unless acted upon by an external force. So now we will look at the second one, which is the time rate of change of momentum of a body is equal to the magnitude of the applied force and acts in the direction of the force. So which law we are talking about? This is the second law of motion, okay? And the governing equation of this law is F is equal to ma, where F is the force, m is the mass, and a is the acceleration, and that is linear acceleration. Okay, the third law is for every action there is an equal and opposite reaction. That is the third law of motion, which is proposed by Newton. Okay, so in the first law, what's written? If we have a car, okay, so this car will remain at rest unless we apply a force, and when we apply a force, what will happen? An acceleration will be produced in the car which will be proportional to the applied force. And if we have a moving car and if we apply the same force in the opposite direction, what will happen? The car will be stopped. Okay, so this is first law of motion proposed by Newton. So if we look at the second law, it says the time rate of change of momentum of body is equal to the magnitude of the applied force and acts in the direction of the force. Okay, so now we will look. This is a bit different from the actual law which we studied in our uh, earlier classes. Okay, so that is actually says the force is equal to mass and acceleration. But here we are talking about the time rate of change of momentum. Okay, so now we will see how the time rate of change of momentum is equal to the magnitude of the applied force. Okay, so we know that momentum is what? Momentum is basically the product of mass and velocity, right? Okay, so we have the momentum available, and we denote the momentum with the letter P, and we denote mass and velocity with the letters M and V, small m and small v respectively. Okay, so since mass m of a body is constant, so mass is a property which remains constant irrespective of the time. Okay, so since m is very much a constant property of a body, so if we want to calculate the time rate of change of momentum, then which quantity of these will change? Mass is not going to change, so the velocity is going to change. So if the velocity is changing with respect to time, what will happen? This momentum will going to change with respect to time, which means we will get the time rate of change of momentum. Okay, so rate of change of momentum is equal to mass multiplied by rate of change of velocity. So we can write it like this. We have a delta P, which is time rate of change of momentum, which is equal to mass multiplied by time rate of change of velocity. And what is this time rate of change of velocity equal to? This will be equal to the acceleration. Since we are talking about linear velocity, so what we will get? We will get linear acceleration, because time rate of change of linear velocity is equal to linear acceleration. So delta P will be equal to m into a, and we know that F is equal to ma, so we can say that time rate of change of momentum is equal to what? Is equal to the applied force. Okay, so we will move forward, and we will discuss the third law, which says for every action there's an equal and opposite reaction force. Okay, so once again we have a car, and there is a force applied on the car. Actually, this force is coming from inside the car, which this force is coming from the engine of the car, but we are denoting that force with the help of this arrow. Okay, so what will happen if we apply the force to this car? It will move and it will collide with the building. Okay, so it is moving with a particular acceleration and it will exert a particular force on this building. So what will happen? The building will also exert the equal and opposite force, and because of that force, what will happen? The car which was moving earlier will now stop, and we have two forces. One is the force of the car and the other one is the force of the building. These two forces are equal in magnitude but opposite in direction. Okay, so this is actually the third law of motion, Newton's third law of motion. Okay, so this is something which you already know, but there's a quick recap of that one. Okay, so now we will discuss about the two subclasses of dynamic problems. Okay, so we deal with two type of problems when we do the dynamic analysis. One is the forward dynamic problem, and the other one is the inverse dynamic problem. Okay, inverse dynamic problem is also known as kinetostatics. So in the first one, the forward dynamics problem, what we have, we already know the forces and torques which are actually exerting on the system. Okay, we know the forces, we know the torques, and what we do, we actually calculate the motion parameters like velocity, displacement, acceleration. So we calculate those. Okay, so that is the forward dynamic problem. It means the dynamic analysis is carried initially, and then we do the kinematic analysis. Okay, so that is the forward dynamic problem. So in this course we are not going to perform these kind of problems. We are going to perform these kind of problems which are known as inverse dynamic problems. Okay, so in this one what we have the acceleration, velocities, and displacement of the system already known, and what we want to calculate, we are going to calculate the magnitudes and directions of forces and torques, okay, which are unknown. So it means the output of the kinematic analysis will become the input for the dynamic analysis. Okay, so we are going to focus on this kinetostatics problem. Okay, so now we will see, or we will discuss what is a dynamic model. Okay, so dynamic model, while developing the dynamic model, what we do, we basically create a very simplified model of a complicated part, or a complicated system which consists of various parts. So if we have a part which is very complex in shape, and which is something actually not exactly the shapes which we study in the math. So what we need to do, we need to simplify that part, we need to simplify the shape of that part, so that made we can make a dynamic model. Okay, so basically the dynamic model is a collection of point masses connected by massless rods. Okay, so basically you know that if we have a object, if we have a part, so its mass will be distributed according to its geometry. Okay, but every mass, every part will have a center of gravity where all of its weight or mass will act. Okay, so in the dynamic model, in the simplified dynamic model, what we do, we replace the original shape of the part with a point mass. Point mass means the whole body, the whole weight of the mass is actually acting at a point. Okay, and that point is basically connected with a massless rod. So the actual shape or actual part is replaced by a system which just have a point mass, and that point mass is connected with a massless rods. Okay, so we will discuss this dynamic model in detail in the coming slides. Okay, so if you have any confusion so far in understanding or in realizing what is a dynamic model, so your questions will be cleared in the coming slides. Okay, so now we will see the dynamically equivalent model of the original body system should have. Okay, so now we have two systems. One is the actual or original system, which consists of many parts or many links, and we have another system which is a simplified system, and a simplified system which we call the dynamic model or equivalent dynamic model. So there are few things which should be common in these two systems. Which two system? The original system and the dynamic equivalent of the original system. So there are three things which should be common or which should be equal, and those three things are: number one is the mass. It means the mass of the original system or original part should be equal to the mass of the dynamic model, number one. Number two is the center of gravity of the original system and the center of gravity of the dynamic model should be at the same location. And the number three, number three is the equal mass moment of inertia. It means the mass moment of inertia or the second moment of inertia of the original system and the dynamic model should be equal. Okay, so these are the three conditions for the validation of dynamic model. Okay, so if the mass of the dynamic model is equal to the mass of the original system, and if the center of gravity of the dynamic model is exactly at the same position, same equation as the original system, and if the second moment of inertia of the dynamic model is equal to the second moment of inertia of the original part or original system, then the dynamic model is a valid dynamic model. Otherwise, it will not be a valid dynamic model, and it will not basically replicating the original model. So now we will discuss something about the mass. Okay. So we know that mass is the invariant property of a rigid body. It means mass of body does not change whether we are on earth, whether we are on a mountain, whether we are out in the space. So the mass is not going to change. So this is invariant property of a rigid body. On the other hand, we have weight, which is actually equal to the mass multiplied by the gravitational constant. So this is that is a property which can vary, and it varies according or depending upon the value of gravitational constant. Okay. So in order to make the dynamic analysis a bit easier, what we will do, we will consider mass instead of the weight right throughout the dynamic analysis. Okay, so mass of links remains constant with time. Okay, so we did the same while discussing the Newton's second law of motion. Okay, so when we were trying to get the time rate of change of momentum, so we put the mass constant, and then we will what we will do, we actually take the time rate of change of velocity in order to get the time rate of change of momentum. Okay, so the things which we are talking about, like in which the mass of a system is constant, it is true for all the machines and mechanisms which are manufactured or designed to be used on earth, on the face of the earth, on the surface of the earth. Okay, because if we go beyond the earth, what will happen? The gravitational constant will change, and that will change the weight. Okay, and there's another thing which can actually change the mass of a machine or a system. For example, if we have an automobile and if we put the fuel in it, okay, so what will happen as we run the car or we drive the car? What will happen? The fuel will be consumed, and there will be a small change in the mass, but that change in mass is so small that we can neglect that mass. Okay, so for all the earthbound machines, we are assuming that mass of the system is going to be a constant parameter. It is not going to change. Okay, but if we talk about the machines which are designed to be used outside the atmosphere of the earth, so those machines are basically uh, in those machines the mass is not an invariant property, or you can say that the weight of a system is not an invariant property. It keeps on changing because the g value of g changes. The another reason for space-bound machines to change its mass is because when we talk about the space shuttles, so when we actually uh, when the space shuttle starts its travel or journey, what just happened? A lot of fuel is consumed, and during the course of its motion, what this space shuttle does, it removes a lot of its part. Okay, so that it can reduce its weight and it can increase its acceleration. So this is a type of machine in which we cannot assume the mass of the system to be constant. Okay, so since we are going to talk about the machines which are going to be used on the earth, and we are assuming that the mass of those machines or those parts is going to be a constant parameter. Okay, so once again we have the kinematic analysis. We know the position, velocity, acceleration. In the dynamic analysis, what we will do, first of all, we will assume the masses. Okay, so now what we are having, we got the value of this acceleration from this dynamic analysis, and now we are in the domain of dynamic analysis. Okay, so in order to get the value of f, we know that f is equal to ma. We know a, we need to calculate the force, but before that we need to assume the masses of links, because in the kinematic analysis we did not discuss anything about the mass of links or the mass of different parts. We considered those links to be massless, right? So in order to start the dynamic analysis, although we have the acceleration, there's another task which we need to perform, and that is the assumption of the masses of the links. We need to assume that the parts which we have has this much of mass. Okay, so number one, we need to assume the mass. If we assume the mass, if we have the acceleration, so what we will do, we can easily calculate the force using the Newton's second law of motion, which is F is equal to ma. Okay, then it will keep on, we need to keep on changing the assumed masses. Okay, why? Because we need to fix this dynamic force at a particular level. There's a threshold value, okay, at which we need to fix this force, because if this force go beyond a particular value or level, what will happen? There will be deflections in the parts. Okay, we are assuming we already uh, selected a material as well. Okay, so if we have the material selected, if we assume the mass, if we have the acceleration, so what we will get? We will get a dynamic force. And with the help of the value of the dynamic force, we can calculate how much the parts will be deflected when that dynamic force will be generated inside the system. And then we need to compare that deflection with the yield strength of the material. Okay, and we also need to look at the other changes or other forces which will be generated due to those deflections. Okay, so if a body is moving, for example, if we have at the rim of the car which is changing its shape due to the applied force, there's a very heavy force applied on the tires, so what will happen? It will change its shape a bit, but that change is still in the elastic limit. It means when we remove the force, it will convert, or it will reverted back to its original shape. Okay, but the thing is, the object or the part is still deflected. There is some change in the shape. Okay, so if the deflection is you can say that out of the limit, or it's changing the actual working of the machine, or it's affecting the actual working of the machine, and we are not getting the motion or the forces which we want to have, and the direction of forces which we want to have, so what we will do, we need to limit those forces, because if the force is less, if the dynamic force is less, what will happen? The deflections will also reduce. Okay, so how we can reduce these forces? So these forces, we know that is a product of mass and acceleration. So either we need to reduce the acceleration, or we need to reduce the mass. Since the acceleration is very much finalized in the kinematic analysis, so the only thing which we have to change is the mass. Okay, so in order to reduce the dynamic forces, what we need to do, we need to keep on changing the values of mass in our iterative process, so that we have the value of dynamic force within the acceptable range or limit. Okay, so then we have the shape and sizes. So in the kinematic analysis, we did not discuss about the shapes and sizes of the links or parts. Okay, because we were assuming the links are shapeless and massless. Okay, so what you need to do, after assuming the mass, you also need to assume a reasonable shape and size of links or parts. Okay, you need to visualize that this part will be of that shape, and that those will be the dimension of that part. Okay, so that is an assumption, and what we will do on the basis of that assumption, okay, we will discuss that later. So there's another thing which you need to select, and that is the material. Okay, although I said that we selected the material in dynamic analysis, but it doesn't matter whether we select it here or here, but we need to select the material as well, because if we select the material, only then we will be able to understand or judge whether the deflections are within the acceptable range or not. Okay, so now we have the assumed mass, we have the assumed shape and size, we have assumed material. So now what we can do, with the help of this shape which we just assumed, we can calculate the volume, right? We can calculate the volume of links or parts. Okay, so if we have the volume of a particular link or part, what we can do, we can multiply that volume with the density, mass density, to get the actual value of mass. Okay, so this was the assumed value. This was the assumed value. This is assumed shape. So on the basis of assumed shape, what we are doing, we are actually getting the volume, and we are multiplying that volume with the density of a material which we selected, and then we get the actual mass of the part. So if this mass is very high, what will happen? The force, dynamic force, will be high. So then what we need to do? We need to either reduce the volume by changing the shape, or we need to change the material. Okay, because we cannot change acceleration, we can only change the mass. These are the different or several activities which we are going to perform in the dynamic analysis. Okay, so now we'll move forward, and this is a table which is mentioned as appendix B in the book which we are studying, the Norton book. And what we have in this table, we have different type of materials. Okay, and then we have the different properties, material properties of those materials, whether they are metals or alloys. Okay, so the material property which we are interested in right now, or at this point of time, is the mass density, which is denoted by rho. Okay, because we can calculate the volume of the links, and then we need to multiply that volume with this density. So in this way we can get the value of mass, and if we have the value of mass, if we have the value of acceleration, then we can calculate the value of dynamic forces. Okay, so there is no need to read those values, but you should know which value is like relevant to the dynamic analysis. Okay, so next one is readjusting mass. Okay, so this is something which I already explained to you, but we will discuss it once again. So if the deflection of parts under dynamic load limit design even at low stress levels, it means although the stresses which are produced due to the dynamic forces are way lower than the yield strength, okay, it doesn't mean that it qualifies or our design is qualified, because although we are still in the elastic range, but some deflection will be produced, and those deflections can actually affect the working of the machine. It depends what is the purpose of the machine. Okay, so how we can further reduce those deflections? The only way is what? To reduce dynamic forces. So if we have to change or further refine the design in the static problems, what we do, if we are like getting a lot of forces or reaction forces in static problem, what we generally do, we actually add mass to make the structure more strong so that it can withstand all the forces which are involved in the working of the machine. But in dynamic analysis, if we add further mass, what will happen? The dynamic forces will further increase. So we cannot do it like this. So the approach in the dynamic analysis is different than the approach which we do in the static analysis or static design. Okay, so if we add more mass, what will happen? It will generate more acceleration. What will So basically, if we add mass, what will happen? We will get higher values of dynamic forces, and because of those higher values, we will get higher deflection values, and the thing is, the machine will not be able to perform the way it should be. Okay, so solution is what? To remove mass in right place. from parts to reduce stresses and deflections. Okay, so in dynamic analysis, in order to further tweak the design, what we need to do, we need to remove the masses at particular or at definite points from the definite locations. Okay, so in this way we can further improve our dynamic, we can further reduce the dynamic forces, and we can further improve the dynamic performance of the machine or a system or a mechanism. Okay, so we will see how and from where we can remove the masses when we discuss the topic of balancing. Okay, so in order to carry out the dynamic analysis in the most professional way, one should know different aspects of mechanical engineering or different subjects of mechanical engineering. You should have the knowledge of materials. You should have the knowledge of the mechanics of materials, and you should have the knowledge of the dynamics. Okay, so only then you will be able to actually analyze the results which you are getting from the dynamic analysis. Okay, so this is something which is not, which you can not do in isolation. So this is something which is actually carried out with the help of the knowledge of the other subjects which you already studied in your earlier semesters. Okay, so we need to have the knowledge of these subjects if we want to design, shape, and size the parts properly with minimum masses, with sufficient strength, and with minimum dynamic forces. Okay, so if we have the knowledge of these subjects, only then we will be able to design our system with the minimum mass, maximum strength, and acceptable dynamic forces. Okay, so now what we will do, we will discuss the mass moment. What is mass moment? Okay, so let's look at the system. So we have this part or this link or maybe this object which is there in a space which has three axes. Okay, x, y, and z axis. And instead of considering the whole mass or the whole part, we are just considering a small part of it. Okay, a differential element of this part, and that differential element is denoted by dm, differential m. Okay, that is a small part of the whole mass. Okay, so what's mass moment? Okay, when mass of object is distributed over some dimensions, it possesses moment with respect to any axis of choice. Okay, so what is this? Because of that moment or because of the mass of the object, what will happen? It will try to rotate around an axis depending upon the situation. Okay, so what will happen? Because of the mass, it will try to rotate around a particular axis. So that property is known as mass moment. It depends which axis we are talking about or which axis we are interested in. So mass moment is also known as first moment of mass or differential element is equal to what? That is equal to the product of its mass and its distance from axis of interest. So that is equal to the mass moment. So like we just saw in the diagram, we have three axes. So it means we need to calculate the mass moment with reference to these three axes. Okay, so we have dmx, which is the mass moment with respect to x-axis. Okay, that will be equal to what? That will be equal to the mass itself. So since we are talking about differential part of the mass moment, so what we will do, we will consider, since we are considering the differential mass, so what we will get, we will get the differential mass moment. And how we will get this differential mass moment? If we multiply the differential mass with this dimension. This dimension, what's this dimension? That is this x, the distance of this differential mass element along the x-axis. Okay, And if we talk about the y-axis, then what will happen? We will take the distance along the y-axis and multiply it with differential mass. And if we talk about the mass moment along z-axis, then what we have to do? We have to multiply the distance along the z-axis with the dm, or differential mass. Okay, to obtain mass moment of body, what we need to do? We need to integrate the equation which we just have, because in that equation we did not consider the whole part or the link or the body. We just considered a differential part of it. So in order to get the mass moment of the whole part, what we need to do? We need to integrate the equations which we derived in the previous slide. So what we will do, we have to take the integration of this x into dm in order to get the total mass moment of a body along or with reference to x-axis. Same is the case with y and z-axis. Okay, so if mass moment with respect to particular axis is numerically zero, so what does it mean? It means axis passes through center of gravity of that object. Okay, only then the mass moment will be equal to zero. Okay, so if the axis of interest passing through the CG, or center of gravity of an object, then what will happen? Its mass moment will be zero. Why? Because there will be no moment arm. We have the force, we have the mass available, but we don't have the moment arm. So if there is no moment arm, we will not get any moment. So that's why if the axis of interest is passing through the CG of a particular part, then the mass moment is equal to zero. Okay, so the topic of mass moment is still continuing. Okay, so if we this is another fact. If we add up all the mass moments, okay, which we are getting at different axes through CG, then it will be equal to zero. Summation of first moments about all axes through CG is zero. Okay, locate CG of all moving parts in a machine or mechanism. Linear acceleration component of each body is calculated at CG. Okay, so these are different facts, which some of which we know and some of which we will apply while doing or while carrying out the dynamic analysis. So what are the steps? Number one, we need to locate the CGs of all the parts, all the links, all the bodies which are actually making the machine or a mechanism. Okay, and those CG, what will happen? The linear acceleration which we calculated in the kinematic analysis will act at those CGs, center of gravity. Okay, then we can model the complicated part as several interconnected simple shapes. Okay, so I just told you that we need to locate the CG of all the parts. Okay, so you know that the parts of machine can be complexly shaped. So it is not mandatory that all the parts of a machine or a mechanism will have a rectangular or square or prism or sphere like or maybe cylinder like shape. It can be of any shape. Okay, so in order to calculate the CG of irregular shape, it is a very cumbersome or very difficult process. So what we need to do, we need to convert, or we need to divide a complex shape into a combination of simple shapes, or the shapes of which we have some formulas available, so that we can easily calculate CG, we can easily calculate the mass moment, we can easily calculate the other properties like second moment of inertia or mass moment of inertia, and we can easily calculate radius of gyration. So these are the different properties which we need to calculate before carrying out the dynamic analysis. And in order to calculate those parameters, we need to locate the CG. And in order to locate the CG, we need to convert the complex shapes into simple shapes so that we can apply the already developed mathematical formulas to calculate the value of CG. We will we will see in the later slides how we can do it when we apply all of this discussion to the example of hammer, how we can calculate the CG of hammer, which is actually a combination of two different parts. We have the head, which is a metallic part, and then we have a handle, which is the wooden part. So we will see how we can calculate the composite CG of that particular hammer. Okay, so if we convert or if we divide a complex shape into simple shapes, so what will happen? It will be easy for us to compute the masses and location of CGs. Okay, and if we have the location of CGs of all the parts, then it will be easy to locate the CG of the whole system or the whole machine or the whole mechanism. Okay, so now this figure is also from the appendix of this book, of the textbook. So in this book what we have, okay, in this figure what we have a regular shape which is known as a rectangular prism, and there are different properties which are mentioned here. For example, this is the volume. So if we need to calculate the volume of this shape, what we need to do, we need to multiply all of its three dimensions with each other, and in this way we can calculate the volume. And if we need to calculate the mass, what we need to do, we need to multiply this mass, oh sorry, we need to calculate we need to multiply this volume with the mass density. It means we need to select the material of this rectangular prism, and then we need to basically have the value of the mass density, and then we need to multiply the mass density with the volume in order to get the mass. And then what we need to do, if we want to calculate the x component of the CG of this particular shape, how we can do it? We can calculate it by dividing the x dimension of this shape by 2. Okay, so if we want to calculate the y component of the CG, what we need to do, we need to divide the y, this is b, this is not h, we need to divide the y dimension of the part or the rectangular prism in the y direction by 2. Same is the case with the z component of the CG. And then these are what? These are the second moment of inertia formulas, and these are the formulas for the radius of gyration. So these are some parameters which we still need to discuss. So when we discuss those parameters, then we will discuss these things. But right now you should know what is this x CG, y CG, and z CG. So these are the three different components of center of gravity of that particular part. So this is prism. In the same way, we have the formulas for cylinder, we have the formula for hollow cylinder, then we have the formula for a right circular cone, we have the formula for sphere. So now what we are going to do, we are going to apply all the things which we already studied on the example of hammer. Okay, so what we have, what's this? This is a hammer. It consists of two cylinders. So this is a wooden handle which will be very much light in weight relatively. Okay, and then we have this metallic part which is known as the head of the hammer. So this part, although small, it has shorter dimensions as compared to the handle, but this is very much heavy as compared to this one. So mass of this one is like maybe uh, tens of times of this mass. Okay, so now we need to locate what? We need to locate the CG, the center of gravity of this hammer. Okay, so we will start. So first of all, what we need to do, we need to define the coordinate system. So we have two coordinates, at least two coordinates, which are this is the x coordinate, which is shown by the axis xx, and then we have the z axis, this the z axis, which is denoted by zz. There is a y axis also which is coming outside this slide. Okay, but that is not mentioned on this slide. Okay, so we have two axes, x and z. What else we have? Okay, we have a CG. CGH means that is the CG of the handle. So we know that it is very easy to locate the CG of cylinders. It is half of the height of cylinder or half of the length of the cylinders. Okay, so this is the CG of the handle. Same is the case with this one. This is the CG of the head. Head is denoted by the letter small d. So we have the CG of the hammer. Oh, sorry. We have the CG of the handle. We have the CG of what? CG of the head. And there should be a CG which is known as the composite CG. But we don't know where it is actually on the coordinate system. We don't know the distance of this composite CG from the axis of interest. This Z is the axis of interest. Okay, so we want to calculate the mass moment with respect to this axis, and we need to calculate the value of the composite CG with respect to this axis, and we need to define this CGH and CGD with respect to this axis, which is axis ZZ, and that is also the axis of interest. Okay, what else we have? We have another axis which is passing through the center of gravity of the handle, and we denote that axis with the letters H. Okay, then we have another axis which is passing through the composite CG, and we denote this, and we denote that axis with the letter G. We have yet another one which is passing through the CG of the head, and we denote it with the letter D. Okay, so these are the different CGs, and the axes are passing through those CGs, and all of those axes are actually parallel to the axis of interest, which is ZZ axis. Okay, so what else? we have we have a reference line. This is not an axis. This is a reference line which is parallel to the axis ZZ, and which is located at the end of this wooden part or wooden handle. Okay, that is the end of it, irrespective of the fact that whether this handle is intruded into this head or not. Okay, so there is only way that this handle can hold this metallic part if that handle is intruded inside of this head. Okay, so we have this axis or reference line which is located at the one edge of this wooden handle, and we have the axis of interest on the other edge. Okay, so this is, what is this? Now we have another parameter which is mh, that is the mass of the handle. Then we have another parameter which is known as md, that is the mass of the head. What else we have? We have RH, that is the radius of the handle, and we have RD, which is radius of the head. Okay, so now what we can do, we can locate those CGs with respect to that axis of interest. So what is the distance of CGD from the axis of interest? This is LD. This is something which we can calculate. Okay, this is something which we can easily calculate because we can locate this CG. We have this axis of interest available, and we can easily measure the distance between these two axes. Okay, then we have what? LH, small LH, that is the length of the wooden handle. We can calculate, we can measure this length quite easily because this is something which is physically available, and we know these two axes which are at the two edges of this wooden handle, and we can easily calculate the length of this wooden handle. Okay, the third dimension is LH by 2. Okay, that is basically the distance of center of gravity of the handle from the axis of interest. Okay, so you can see that all of these dimensions are started from the axis of interest. Okay, so this is the distance of CG from ZZ. We have another one which is D. So now that is the composite CG, the distance of composite CG from the axis of interest. So now what we will do, once again, this is the hammer. So in this slide, there is one unknown. We cannot measure this composite CG by measuring the dimensions of the actual hammer. Okay, it means we need to calculate, or we need to use the formulas to calculate this value of D, which is the distance of composite CG of this whole hammer with respect to, or with reference to, this axis of interest ZZ. Okay, so now what we will do, now we will develop, or we will replace this hammer with a dynamic equivalent model. So how we can do it? So this is the hammer. Once again, we have the x-axis, we have the z-axis. This is the composite CG, and there is a axis which is passing through that composite CG, and we denote that axis with the letter G. Okay, so this is the equivalent dynamic model of this hammer. So what we have in this equivalent dynamic model? We have two things. One is this black rod, which is considered to be massless. It means this is a rod which is massless. And then we have a point mass, although it has some dimension, but actually it doesn't have any dimension. This is just a point. This is just a point at which the whole mass or whole weight of this hammer is acting. Okay, so consider it just a point. Okay, and we have an axis passing through that point, because if I put a point here, it will not be able to visualize, you will not be able to see it. So that's why instead of putting a point uh, uh, along with this rod, what we have to do, we have to make a sphere or circle, so that we can say that this is the point which we are talking about. Okay, and the mass of this point, or the actual mass of this point mass, is basically the sum of the mass of the handle and the head. Okay, so initially we actually validated the dynamic model, and we said that the mass of the actual system and the mass of the dynamic equivalent should be equal to each other, and the mass moment should also be equal. The CG location should be the same. Okay, so what else we have? So this is another parameter which is introduced, and that is K, which is known as radius of gyration. Okay, so this is the radius of gyration. So when we use the dynamic equivalent model, so instead of using the composite CG, what we use? We use actually the point mass, and the distance of that point mass from the axis of interest is equal to the radius of gyration, which is denoted by the letter K. Okay, so this is radius of gyration. We also don't know the value of this K. We don't know the value of D, which is the distance between the axis G and Z. We need to figure out how to calculate those lengths D and K. So first of all, what we need to do, we need to add the mass moments of individual components, which are handle and head about the z-axis, and set it equal to the mass of moment of equivalent dynamic model about zz. Okay, so how we can do it? Summation of all the mass moments, and that will be equal to what? That will be equal to the mass moment of handle, mass moment of what? This is the mass moment of head, and we need to put this equation equal to the mass moment of dynamic equivalent of the system. Okay, so we know that the formula of mass moment is what? Mass multiplied by what? The distance. It's distance from the axis of interest to the CG of a body. So this LH by 2 is the distance of CG of a handle from the axis of interest. This LD is what? That is the distance of center of gravity of head from the axis of interest ZZ. And what's this? This D is actually what? This D is the distance of composite center of gravity of hammer. So we have one unknown and we have one equation, so we can easily find out the value of D, which is the distance of composite CG from the axis of interest. So all of the other parameters are already known, so we can easily, so this D should not be here, right? Okay, so this is how you can calculate the composite CG of a system, provided you convert the complex shapes into simpler shapes. Only then you will be able to locate CG. Otherwise, it will not be able to locate CG of the whole system, because you don't know the CGs of the individual parts. You will only be able to calculate the CGs of individual parts if you convert those irregular shape into regular ones. Okay, so y and z components of composite CG are both 0. Why? Because we know that if we talk about cylinder, so that CG is only acting on the one axis. It doesn't have the y and z components. All of those components are 0. If we talk about the CG of cylinders, that is not the case with the other regular shapes. Okay, so now we need to study the mass moment of inertia. Okay, so what is mass moment of inertia? So before going to the mass moment of inertia, we need to recap once again the second law of motion. So if we apply the second law of motion to the translational system, so what is the equation? Equation is like this. We have the F is equal to ma, where F is the applied force, m is the mass, and a is the linear acceleration. But if we apply the same second law of motion to the rotational system, so what we will have, instead of force, now we will have the torque. Instead of mass, now we will have a new parameter I. We don't know what's this. And instead of a, which is linear acceleration, we will have angular acceleration alpha. Okay, so this I is a constant of proportionality, and we need to figure out what is this. It seems like this is the mass moment of inertia. Okay, so T is the torque, then we have I, which is mass moment of inertia, and then we have alpha, which is the angular acceleration. Okay, so this is the application of second law of motion to the rotational systems. Okay, so mass moment of inertia is measured with respect to the some axis of rotation. Okay, same is the case like we studied in the mass moment. So it is measured with respect to some axis of rotation or axis of interest. Number one. Okay, usually axis of rotation passes through CG. Okay, so in this case, in case of mass moment of inertia, the axis of interest generally pass through CG. It can be a CG of a particular part. It can be a CG of a complete mechanism or complete machine, composite CG of the machine or the mechanism. Okay, so mass moment of inertia of differential element, what's product of its mass and square of its distance from axis of interest. Okay, so in case of mass moment, what we have, we need to multiply the mass with the distance between what, between this axis which is passing through the CG and axis of interest. But here what we need to do, we need to multiply the mass with the square of the distance between the axis passing through the CG and the axis of interest. Okay, so this is a bit different from the mass moment. Okay, so differential element of mass moment of inertia along or across x-axis would be equal to what, rx square multiplied by dm, and we can denote this thing equal to what, equal to y square plus z square dm. So if you look at the shapes which I showed to you in the first part of the lecture, you can easily locate what are those y square and z square, and how we can replace this rx or the x dimension with these two dimensions. Okay, so this, the formula for ix changes for different irregular shapes. So if we talk about the y-axis, the formula will become ry square multiplied by dm, which is the differential mass element, and that will be equal to x square plus z square. In the same way, we have the iz, which is the mass moment of inertia across z-axis, and that will be equal to rz square multiplied by dm, or is equal to x square plus y square into dm. Okay, so if we integrate the equation which is showed to you in the previous slide, what we can get the actual value or the value of mass moment of inertia or the whole part or the whole link or the whole machine. Okay, so we just need to integrate. So this is ix, this is iy, and this is iz. Okay, so we are discussing the mass moment of inertia with the help of a example of a hammer. Okay, so what is actually mentioned in the passage is that if you hold the hammer far away from the head, what will happen, you need more torque or more energy to lift the hammer. Okay, you need to apply more energy to lift the hammer because the mass moment of inertia is high. And what you will get in return, when if you able to lift the hammer, so it will have more energy, it will have lot of kinetic energy. And when you will strike that hammer in the reverse motion, if it means if you lift it and then if you once again allow it to drop on the nail, what will happen? All the kinetic energy which is supplied by a person who is lifting the hammer will be exerted on the nail. Okay, so it means it will have higher kinetic energy. So if you hold the hammer far away from the head, you need more energy, and in return the hammer will exert more energy on the nail, and you will be able to drive the nail, or you will be able to drive the nail more effectively. Okay, so this is something which is mentioned about the mass moment of inertia. Okay, so we will move forward, and the topic of mass moment of inertia is still continued. Okay, so now what we need to do, in the same way in which we applied the concept of second moment of inertia in translational and rotational system, we will now actually modify the equation of kinetic energy which we use for translational system in such a way that we can use the same equation for the rotational system. So the kinetic energy equation for the translational system is equal to what? That is equal to half mv square, where m is the mass and v is the linear velocity. Okay, and if we want to get the kinetic energy from a rotational system, so we need to modify this equation a bit. So instead of mass, what we will have? We will have the mass moment of inertia. And instead of v, linear velocity, what we will have? We will have omega, which is angular velocity. So in this way, we can calculate the kinetic energy of a rotational system. So that is basically the product of the moment of inertia, mass moment of inertia multiplied by the square of the angular velocity and divided by 2. Okay, so that's good. Okay, so we will continue talking about the mass moment of inertia. So now we are in the state or in the position to define the mass moment of inertia. So the mass moment of inertia is the ability of the body to store rotational kinetic energy and is an indicator of the amount of torque that will be needed to rotationally accelerate the body. Okay, so this is something which we already discussed in the passage. So after listening or after understanding those passages, we devised a definition of mass moment of inertia, and that is the ability of the body to store rotational kinetic energy and is an indicator of the amount of torque that will be needed to rotationally accelerate the body. Okay, the amount of energy, kinetic energy, which you need to lift the hammer. Okay, so if it's a big hammer, sledgehammer, then maybe I will not be able to uh, lift it because I'm still a child, and since you are young fellows and you might be able to lift that hammer. Okay, so there's another definition of this mass mode of inertia, and that is the measure of resistance to angular acceleration. Okay, so the same thing is explained with fewer words. And now we will discuss or talk about the units of mass mode of inertia. So that is pound, inch, second square if we talk about the imperial system, and it is Newton meter second square if we talk about the SI system. Okay, so let's go forward. Okay, so now we have a next topic, which is the parallel axis theorem or transfer theorem. So this theorem is used to transfer the mass moment of inertia or moment of inertia from one axis to the another. Okay, so let's say if we have the moment of inertia calculated at the CG of a particular part, and we need to shift that moment of inertia to other axis, which is axis of interest, then we need to use this parallel axis theorem. Okay, so moment of inertia of body with respect to any axis zz is the sum of its moment of inertia about an axis gg passing through its cg and parallel to zz, and product of mass and square of perpendicular distance between parallel axes. So this is something which we cannot understand, so we need to read it once again. So what is the mass or what is the moment of inertia of body with respect to any axis zz? you need to keep in mind that that axis zz is the axis of interest. So moment of inertia of a body with respect to any axis of interest is equal to the sum of, so it means it will have two terms. The first term will be the moment of inertia about an axis GG. It means, first of all, we need to calculate the moment of inertia of that particular part or a machine or a mechanism about its own CG. Okay, so if we know that one, if we know the CG of a part about its own, if we have the moment of inertia of a part about an axis which is passing through the CG, then we can calculate the mass moment of inertia, or we can shift it to another axis of interest. So the uh, second term will be the product of mass and square of perpendicular distance between parallel axes. Okay, so we will have two terms. We are talking about the mass moment of inertia which is passing through axis of interest ZZ. So that will be equal to mass moment of inertia of a part which is passing through CG and denoted by IGG, and then we have to add what? We need to add the mass, we need to add a term which consists of the product of mass of the part multiplied by square of the distance between the parallel axis. It means axis ZZ, which is the axis of interest, and axis GG, which is the axis which is passing through the CG of the part, are parallel to each other. So in this way, what we can do, we can shift or we can calculate the mass moment of inertia, the value of mass moment of inertia, which we calculated for CG, and we can shift it to another axis of interest, ZZ, and you need to keep in mind that both of these axes should be parallel to each other. Okay. So where ZZ and GG are parallel axes, GG goes through the CG of body or assembly, M is the mass of the body or assembly, and D is what? D is the perpendicular distance between the parallel axes ZZ and GG. Okay. Okay, so the topic continues. The hammer broken into two cylindrical parts, handle with length LH. We already discussed that one. We know what we did to the hammer. We broke it, or we divided it into two cylindrical parts. One was the handle. The length of the handle was denoted by LH, the mass by MH, and radius by RH. Similarly, the length of the head was denoted by LD, mass by MD, and radius by RD. So mass moment of inertia of handle about its CG axis HH, that will be equal to what? That is the formula. There is no need to memorize it. This is something which you derived in your dynamics course or some other course. Okay, so this is very much a formula. There is no need to memorize it. Okay, so, and we are not going to derive this formula in this course. So this is the formula for calculating the mass moment of inertia of cylindrical shapes. Okay, and the axis of interest is passing through the CG of that part. So in this way we can calculate what? IHH. And if we want to shift it, okay, before that we need to calculate what? The mass moment of inertia of the head. So that will once again will be equal to, the formula is the same. We just need to replace MH by MD, RH by RD, and LH by LD. Rest of the formula or rest of the expression is the same, because both handle and head are basically cylindrical parts. So now we need to shift that mass moment of inertia to the axis of interest, which is ZZ. So what we need to do, we need to add what? We need to add IHH. What is IHH? That is the mass moment of inertia of handle, and then add another term which is the product of what? Product of mass of the handle multiply by the perpendicular distance between the axis of interest and the axis which is passing through the CG. Okay, so you know that the axis HH which is passing through the CG of handle, and the axis ZZ has distance equal to what? LH by 2. So that is the distance between the axis HH and ZZ. In the same way, we have the component of the head, and what we need to do, we need to apply the parallel axis theorem to this part as well. This is IDD, which is the mass moment of inertia of the head, which is reference to axis, which is passing through the CG of head. And then we have another term, which is the product of what? The mass of the head and the perpendicular distance between the axis which is passing through the CG of head and the axis of interest, which is ZZ. And that distance is equal to LD, and we need to take the square of that distance. So with the help of this formula, we can shift the composite the composite CG, the composite CG of hammer from the axis which is passing through CG to the axis of interest, which is ZZ. Okay, so now we just need to put the values, and that's it. So in this way, we can calculate the mass moment of inertia of any body or a combination of bodies to axis of interest. Okay, that's fine. Okay, so the next one is once again determining mass moment of inertia. So there are two methods with the help of which we can calculate the mass moment of inertia. So one method is the analytical method, which we just discussed. That is the analytical method. Okay, so in which with the help of the same method we calculate the mass moment of inertia of the hammer. Okay, so the steps which we already followed are mentioned here. Okay, so you can calculate the mass moment of inertia of any body or part or machine with the help of a CAD software as well. There is another method which is experimental method, and in order to use that method, there is a mandatory condition that physical part or the prototype should be available. If you have the physical part available, only then you can use this experimental method to calculate the mass moment of inertia. Okay, so there's a lot of steps which is involved in calculating the mass moment of inertia using the experimental method. It is mentioned in the book, and the example of the connecting rod of an engine is actually uh, quoted in the book, and the author tried to calculate the mass moment of inertia of the connecting rod using this method. Okay, so the next one is radius of gyration. So first of all, we will discuss the definition of radius of gyration. So what is the definition of radius of gyration? That is the radius at which the entire mass of body could be concentrated such that resulting model have same moment of inertia as original body. Okay, that is the radius of gyration. So in the case of, or in the example of hammer, we denoted the radius of gyration with a letter K, small k, and that small k is the radius of gyration, and the definition of radius of gyration is the radius at which the entire mass of body could be concentrated such that resulting model have same moment of inertia as original body. Okay, so now we will see how we can calculate or how we can measure or how we can derive the equation of radius of gyration. Okay, mass and mass moment of inertia of equivalent dynamic model and original body must be equal. This is something which we discussed in the initial slides. That there are three conditions, and two of them are that the mass of the original system and the dynamic equivalent model, and the mass moment of inertia of the original system and the dynamic equivalent model should be equal to each other. Okay. Okay, if IZZ is the mass moment of inertia of original body about ZZ, and M is the mass of original body, then IZZ is equal to what? MK square. What's MK square? MK square is the moment of inertia, mass moment of inertia of the equivalent dynamic model. Okay, this M is equal to what? This M is equal to the mass of the body, and this K is the radius of gyration. So if you multiply the mass with the perpendicular distance between the axis of interest and the CG, then what we have? We have this mass moment of inertia. Okay. So in this way, we can calculate the value of K by simply taking the under root of the fraction IZZ over M. So if we know IZZ, which is mass moment of inertia of any body or a machine or a mechanism, and if we know the mass of any part or machine or mechanism, then we can easily calculate the radius of gyration, K. Okay, so that was something which was missing in the diagram of hammer. Okay, so we already calculated the value of D, so now we calculate the value of K, which is radius of gyration. Radius of gyration converts the original system into an equivalent dynamic model in which the entire mass of the system is replaced by a point mass at the end of massless rod of length k. Okay, so this is something which I already explained to you while we were discussing the hammer example. Okay, so this IgG, we know that Izz is equal to what? IgG plus md square, right? Because IgG is mass moment of inertia of a part with respect to the axis which is passing through CG, and Izz is the mass moment of inertia of a part with reference to axis of interest ZZ which is not passing through the CG. So that should be equal to IgG plus md square. And what is m? M is the mass of the body or the part, and d is the perpendicular distance between these two axes ZZ and GG. Okay, and we have another equation which we just write, and that is equal to Izz is equal to mk square. Okay, so with the help of these equations or by comparing these two equations, what we can conclude? We can conclude that radius of gyration k is always greater than the radius of composite CG, or the distance of composite CG with respect to the axis of interest, which was denoted by D in the hammer example. And this is the last topic of our today's lecture. Okay, so what is center of percussion? So first of all, we will see the definition of this parameter, and that is a point on body which, when struck with force, will have associated with it another point called the center of rotation, at which there will be zero reaction force or zero linear acceleration. Okay, so once again, we need to look at the definition. So, a point on a body which, when struck with force, will have associated with it another point called the center of rotation, at which there will be zero reaction force. Okay, so now what we are doing, we have a body. Let's say we have a bat. Okay, we have a bat and we are going to face a ball which is bowled by a very fast bowler. Okay, so it means that ball is going to come with a lot of force. So what will happen? So when the batsman holds the bat, so that will basically mark the center of rotation, because from that point he is going to rotate the bat so that he can hit the ball. Okay, so that is the point of that is the actually that handling, or uh, that keeping the that holding the bat is actually defining the center of rotation. Okay, so that is one point. And with respect to that center of rotation, there will be another point which is known as center of percussion. We don't know where that point is along the bat. Okay, so if the batsman played the ball in such a way that the ball hits at the center of percussion of the bat, what will happen? He will not feel any force in his hands. It seems like there is no reaction force. Although the ball was bowled at a high velocity and he rotated the bat, and the ball went out of the boundary, but still the batsman did not feel any force, any linear acceleration in his hands. He very comfortably able to throw the ball out of the boundary. It will only be possible if the ball hits a particular point which is known as a center of percussion, and that particular point changes when we change the position of holding the bat. It means we are talking about the pair of points. Okay, pair of points. If we change one point, the other point will also change. Okay, and if that large force is acted upon, okay, there's another ball which is bowled by the same bowler, and the same batsman is facing the ball, but now he is holding the bat at some different position, and the ball, he was not able to hit the ball at the center of percussion of the bat. So what will happen? So now the ball will not go out of the boundary, but instead he will force, he will feel a very stinging force on his hands. Very, you can say that, very harsh force, disturbing force. He will feel vibration in his hands. because that force, the force was not acted on the center of percussion but somewhere else. So because of that force, what will happen? He will feel the linear acceleration. He will feel the force, the reaction of that ball in his hands. Okay. So that is something which is related to center percussion. And now we are going to apply this concept on an ice hockey stick. Okay. So I will try to explain it further with the help of the example of ice hockey stick. So the cases which I just explained to you are mentioned here. Okay. So now what we have an ice hockey stick. Okay, you can see that this is a ice hockey stick, and uh, the axis of ice hockey is along the x-axis. So we have a particular coordinate system in which we have two axes, x and y axis. X-axis is along the axis of hockey, and y-axis is perpendicular to the axis of hockey. And we have the coordinate system defined at the CG of the hockey, right? Okay, what else we have? Okay, then a force is applied at a particular point P. Okay, a linear force is applied at a point P uh, on the hockey. The distance of that point P from the CG of the ice hockey is denoted by LP, small LP. Okay, and we have another point which is R, and the distance of that point R from CG is X. It means if we hold the ice hockey at this point, and if the puck of the ice hockey is struck at this point, what will happen? The holder of this ice hockey will not feel any acceleration. Okay, but we don't know the distance of that point from the CG. Okay, and we don't know the distance of that one if we are playing hockey. But in this example, we know this one, we know this one, we know LP, but we need to calculate XP. Okay, so let's say if we know that the force is going to apply at a particular point. Now we need to determine the second point of the pair, which is the point of rotation or center of rotation, with the help of which we can minimize the reaction due to this force. And reaction force, as a result of this force, will produce a linear acceleration if we do not hold the hockey from this point or at this point. We have another parameter which is m, that is the mass of the ice hockey. Okay, so what else we have? Okay, so when we hit the okay, so now we are assuming that hockey is lying on the field, on the playing field where the ice hockey is played. Okay, so what we are doing, we just drop the ice hockey on the field and we apply a linear force. So what will happen? This hockey will move. So in which type of motion the hockey will move? It will move in complex motion. It will translate as well as rotate. So in the translation, what will happen? The CG will move in the linear motion or translational motion, and there is another motion which will be accompanied by this translation motion, and that is the rotation of this hockey around the axis CG. Okay, so we have two accelerations, which is number one, the translation axis, which is actually the translation of the point CG. The other one is the rotational motion, and that is rotational acceleration, and which will be around the axis CG. It means the hockey stick will move in the straight line, and it will rotate around its own axis as well. Okay, so now we have two accelerations. One is this linear one, which is denoted by AGY. AGY is basically the acceleration of point G along the y-axis. Okay, we can say it like this. And then we have another acceleration, which is rotational acceleration, that is denoted by AT. AT means that is tangential component of the acceleration, and that is denoted by that is equal to R alpha. Okay, so now we will figure out what are the formulas of these terms, and then we will get back to this diagram. Okay, so the linear acceleration of point G along y-axis is equal to what? This is the second law of motion. It means AGY. AG is what? Linear acceleration of point G along the y-axis will be equal to what? Will be equal to F over M. Force with which we hit the hockey stick, and M is the mass of the hockey stick. And what else we have? We know that this angular acceleration is equal to torque divided by IgG. So this is the equation. This is actually the application of second law of motion to the rotational system. So it's the same thing, but now we are applying it to the rotational system because there's a rotational motion also going on in the ice hockey stick, and that is the rotational motion of the hockey stick around its CG axis. Okay, so we know that angular acceleration is equal to torque over IgG, where IgG is what? The moment of inertia of a particular body with respect to the axis which is passing through CG, center of gravity. Okay, we also know that the torque is equal to F into LP. Why this F into LP? Because we know that this force which was applied on this ice hockey, and that of because of that force a torque was applied, and because of that torque that hockey is now in circular motion. So this is force, this is moment arm, and this torque is actually uh, inducing the rotational motion in the ice hockey in combination with the linear motion. Okay, so this torque will be equal to the product of F multiplied by LP. So this torque is equal to F multiplied by LP. It means we can equate those T's, right? And we can calculate the value of alpha. If we replace those T's, so what we can get? We can get the expression of alpha without T. We can replace those T's. And now alpha, which is the angular acceleration, is equal to force, applied force, multiplied by the distance between the point of application of the force and the CG, divided by the mass moment of inertia of the hockey, which is passing through the axis, which is applied on the axis passing through CG. Okay, so this is the angular acceleration. So if we want to calculate the total acceleration which is experienced by the ice hockey, that will be the sum of these two accelerations. Okay, AGY and R alpha. Why we use R alpha instead of only alpha? Because we are talking about, or we are considering the tangential component. So it is the tangential component of the acceleration which is going to rotate the hockey around its axis. So this is the sum of this will equal to the AY total. We know the formula of this one, we know the formula of this one, so we can simply add it. Okay, so center of percussion is the point when no linear acceleration is experienced by the holder of the object. So when there will be no linear acceleration, when this linear acceleration component and this rotational acceleration component are equal to each other and opposite in direction. So what we can do, we can put AY total is equal to 0. We don't want any force to be experienced due to the linear acceleration uh, along the axis of the hockey. So we don't want that one. So if we want to calculate the point at which we need to hold the hockey so that there is no reaction force, then we need to calculate this x. That is the point at which if we hold the hockey there will be no reaction force. Okay, so if we equate this equation, like if we equate the linear acceleration and put it equal to the negative of this tangential acceleration, then we can find out the value of x, and that value of x is the point at which if we hold the hockey there will be no reaction force experienced by the holder of the hockey. Okay, so that x will be equal to what? Minus IgG over MLP. It means that x is the distance. Okay, if we hold the hockey from, or if we hold the hockey at, there will be no reaction force. Okay, so we will go back to the slide once again, to the diagram once again, to explain those arrows which are there in the diagram. But before that, we need to discuss those bullets. So number one, a relationship between center of percussion and the center of rotation involves only geometry and mass properties. You see, there is no other thing in this relation other than the mass and the dimensions and the distance and the mass properties. Okay, so this is the relation between what? The center of percussion and center of rotation. Magnitude of applied force irrelevant. There is no inclusion of the applied force. F is not mentioned in this expression. Okay, what is mentioned only is the point of application or the distance of point of application of the force. That is important, not the magnitude of the force, because eventually that force doesn't matter, because the force is acting on the sweet spot, due to which there is no linear reaction. There is no reaction due to linear acceleration. Okay, there is not just one center of percussion of body, rather there are pair of points. It means if we talking about a particular hockey, so there is not a particular point which can be defined as center of percussion. Okay, there can be multiple center of percussions depending upon multiple center of rotations. So if we change the center of rotation, or if we change the place from which we are holding the hockey, what will happen? The center of percussion will also change, and the location of center of percussion is actually defined by this parameter x. For every point, for every center of percussion at which the force is applied, there will be a corresponding center of rotation point at which reaction force felt to be zero. So now we will go back to the slide, this diagram once again. Okay, so what we have in this diagram, there are two type of arrows. One are the black arrows and the other one are the red arrows. So these black arrows which are facing downward shows the linear acceleration. Linear acceleration of what? Linear acceleration of the point G. Whereas the red arrows basically showing the tangential acceleration. Okay. So initially, or at any point what we have the combination of these two acceleration, which is actually giving the complex motion to the ice hockey stick. But at few points, like if we talk about this point, there is no rotational component. It means this point will not rotate. This point will only translate, and it will translate with the linear acceleration AGY, because this is the axis of rotation. So axis of rotation only translates. This is CG. It will only translate, and at this point, the acceleration is basically purely what? Purely linear acceleration. And if we talk about the acceleration at this point, which is point R, the center of rotation, at this point, the tangential acceleration and the linear acceleration are perfectly equal to each other, but in opposite direction. So if we have uh, this scenario in which the linear acceleration and angular acceleration are equal to each other, are equal but opposite to each other, then what will happen? There will be no acceleration at this point. And if there is no acceleration, there will be no dynamic force, there will be no vibration, there is nothing. Okay, so it seems like nothing touched the hockey, and he will be able to place the hockey or handle the force without without feeling any stinging force.